Hello, everyone. This is Dave from the Element 14 community, and let me welcome you all to the first edition of our four-part webinar series with Texas Instruments and Würth Elektronik. In this four-part series, we're going to be talking about high-efficiency and low EMI switched mode power supply design. And today, we are really lucky to have Lorandt from Würth Elektronik, who's going to take us through all the different EMI considerations of the magnetic material basics for DC and DC converters. Now, if you have a question for our presenter during the course of the presentation, you can utilize the Q&A function of the WebEx application. You can find that as on the right-hand side, should be a Q&A window drop-down. If you're having any technical issues, you can't hear or see anything, you can feel free to let me know directly at Premier Farnell Webinar via the chat window. There's really exciting things happening with this series. Not only if you attend all four, we'll be tracking that and be sending you out a certificate of completion from TI and Würth, but after each presentation, we're also going to have a quiz for you to take part of. It's just a simple two-question quiz. We'll send at the end of the presentation. Now, what happens if you answer both questions correctly, you'll be put into a drawing to win some great prizes. Today's prizes is a 3-book series sponsored by Würth. Now, if you attend all 4 sessions and answer the quizzes correctly for each of those corresponding webinars, you'll be put into a drawing for an excellent development kit worth over $350 American. So you can find more information about the kit, the terms and conditions, how to apply, all those different things over on element14.com at the registration page on which you registered from. And again, really excited to have everyone in attendance. And we're going to go ahead and start it as I pass the ball over to our presenter, Lorandt, and he's going to take us through a wonderful presentation.
Thank you, Dave. Hello, everybody. My name is Lorandt Fölkel. I'm from Würth Elektronik, application engineer. And I will try to introduce to you today some very simple filters and few basics about magnetics. But first of all, if you are thinking about EMC issues, there are some requirements in an EMC, worldwide, I will say. In Europe, we have plenty of different standards, which I can say it's a lot of different laws and a lot of standards which you have to implement to your device if you want to be compliant with the EMC registration. But there are some approach in a European Union members, then it makes your life a little bit easier. We have 33 new approaches. Just look around about that last week and count them. So it makes it a little bit easier if you are looking on the different laws when your device you want to introduce to the European Union. In fact, it's very simple. You just have to put a CE marking to the device, like you can see here in this picture. But be aware that if you put a CE logo and your device is not fulfill the EMC directive, in some countries you have to pay quite a lot of high penalty. In Germany, I know about something like 500,000 euro if you have been catched from the legislation from this market surveillance. But some other countries, like in the United Kingdom, the EMC law, it is behind the criminal law. So if you put any device to the UK market and it is not compliant with the EMC law, it is like, you can go to the jail. So it's not so funny. How it looks, this CE logo, it is also described in the EMC law. It must be exactly like this C and E. They are touching tangential on one single point. And this is not enough just to put a sticker on it. You have to make additional declaration of conformity. And a lot of mistakes have been done that if you make a declaration of conformity, is very important that even if you are the design engineer of your device, and you sign this paper in thinking, okay, this is everything correct and you did measure it and everything is fine, you have to be careful because it cannot be signed for just anybody in a company. It must be the designer guy or the designer people who are involved, and they are the responsibility of the whole company to sign official letters and make the declaration for, like in the EMC, EMI. Different countries, different continents, like in US, you have to put, you have to be compliant to the FCC law. In Japan, you have to be compliant with BCCI. In Australia, CTIC. In China, CCC. Each country has already kind of EMC regulation you have to fulfill. It doesn't matter which kind of device you're doing, but it must be compliant with the EMC law. What means that for your device, in fact? I have here an example for a radio and TV broadcast receiver, and electronic device need a power supply. And if you go with the EMC lab with your device, they will take care from two different point of view. One of point of view, they will look around what is the conducted emission. So it will be some limits. This is for European legislation. You have the quasi-peak and you have the averaging. And if your DC-DC converter or AC-DC converter met that kind of noise, well, you cannot say this is just a little bit above the limit. They will be not so happy to have that device in the lab, so you have to redesign to put some additional filter. It's not so easy work when you have such big noise. The next point is if you are looking about the radiated emission. You have in the EMC chamber, again, two different limits. It depends now, again, which is your maximum frequency used in your device. If you use a processor which is already tacted by higher like 1 gigahertz, then the frequency will be extended up to 5 to 6 to even to 9 gigahertz. In this case, because it's just simple TV broadcast television, it's 1 gigahertz limit. Then you have two different limits, like here you can see the industrial limit and the home appliance limit. So in industrial environment, it's allowed to make a little bit more noise. In home appliance, should be not that much. Yeah. If you have a device like that, you can say, Houston, we have a problem. We have to do something here because the noise is too big. Let me turn back a little bit, not in time, but in the basic of magnetic field. You know, the magnetic field is very similar like the current. It takes always the easiest way. So if you introduce in the magnetic field a ferromagnetic material, the magnetic field will find the easier way, will bend, and it will go to this ferrite core. And this is not like in the air, which is very straight and very, very nice that you can handle that. But if you describe an induction in the air choke, you may use the formula B, it is mu0 times H. mu0 is a constant vacuum permeability. H, it's also very nice to use that because if you put more current, you have more H, more B, very nice linear function. If you use an inductor or choke based with a ferrite core, then you have to use the formula B, it is mu0 times mu-R times H. Mu-R by the air choke is 1, it's also constant. By a ferrite core-based inductor, you have this initial permeability or called relative permeability. And this point is that this is very, very dependent parameter. This mu-R depends on material, depends on frequency, depends on temperature, depends on current, depends on pressure, and. And now you start to hate inductors. Well, it was similar for myself when I was design engineer and I have to use an inductor. I hate that. I hated to use it in my design, but I must use them. Now I understand much more about inductors and I realized why I made sometimes mistakes. The biggest influence, it is the temperature dependency. You have to take care when you qualify your product, because if you measure the permeability of a ferrite core, like here in this example at 23 degrees Celsius, in ambient temperature 23 degrees Celsius, you may have something like a mu-R of 670. That must be something like a nickel zinc ferrite. Now, you put this device in your climatic chamber and cool down to minus 40 degrees Celsius, your mu-R will drop to 500 something. Now, if you want to qualify to plus 85 degrees, you heat up in a climatic chamber, you may have not more 500, not more 600, you have something almost 800. And now you just try to remember back what was the function of the induction. It is mu0 times this mu-R. This mu-R is so much influenced just by the temperature. So you have to take in consideration this drifting anyway. Additional point, if you have a very, very hot environment, if you are working in a ambient where you can even reach higher temperature like 125 degrees Celsius, there are some components which are qualified to 155 or 160 degrees Celsius. But be aware that sometimes some ferrite core, even they are qualified and withstand a storage temperature of 160 degrees, it could be that they will not operate, because at a certain point, the ferrite, if he reaches Curie temperature, his permeability will drop, and it will drop not to 0, it will drop to 1. So a ferrite, if you're getting very hot, he will lose his magnetic properties. It will act like an air choke. Doesn't matter how high it was this temperature and how long you will keep that outside of this Curie temperature. As soon you cool down and you are below the Curie temperature, the ferrite property will turn back and will be not destroyed. A ferrite is sintered between 800 to 1,800 degrees, so you will not be able to destroy that by heat. Yeah, of course, if you go to the Iceland and you have some volcanoes in Iceland, and then you can put that into the volcano, it will melt everything. But I don't care about ferrite, and you will take care more about the rest of the electronics. Well, this permeability, it is quite a complex permeability. It is also complex to measure. It is not so easy to measure it. First of all, you will need to have something like an impedance magnetic analyzer. We use one of the Keysight and former Agilent. Even if you have this analyzer, you need to invest some money for this fixture and jigs additional. And, well, then it's easy to measure impedances. But even if you have the impedance value, it doesn't tell you anything. You know that you have an impedance. But the impedance actually is a measured value about a fragment above the frequency for XL and R. The XL is the impedance reactance, and the R is the losses himself. So if you just know that you have 200 ohm impedance at 100 megahertz, it doesn't tell you too much. You have to know it is more impedance reactance or it is losses. Why is that so important? If you want to build a DC-DC converter, it's very important that you take care that you have a dominancy of the XL impedance, the impedance reactance. Because if you use different ferrite core material and your switching frequency are something like 150 kilohertz to maximum 200 kilohertz, you can use iron powder core, manganese zinc core, nickel zinc core. But as soon as DC-DC converter will switch a little bit more higher, like 500 kilohertz, at 500 kilohertz, iron powder core will have not anymore the 100% XL, it will have more dominancy of R, and you will see that even if you use a very, very low DC resistance inductor, and the current is not so big, the inductor will start running hot because of the core losses. At 500 kilohertz, you can use manganese zinc or nickel zinc. But you can see already the new generation from Texas Instruments chips, they are able to be switched up to 8 megahertz. At 8 megahertz already, manganese zinc, it starts to be quite very lossy. I would suggest and recommend to use nickel zinc material. Today, we are able already to make this DC converter with 10 megahertz switching frequency, standard. This is switching frequency with that standard IC from the stock from the market directly. 10 megahertz from 10 years ago, it will be something like science fiction, Star Wars or something. But today, it's 10 megahertz very, very usual if you want to build a very high efficient and very small DC-DC converter. Your switching frequency goes higher, and automatically your inductance and capacitor and all the passive components will be smaller and smaller and smaller. But even nickel zinc has its limits, and above 10, 20 megahertz, I will not use any more nickel zinc material for storage of the inductance, for storage material, because he will have too much losses. Typical application are for very, very old, this kind of old national LM series, maximum 150 kilohertz. We still did use this kind of iron powder core. For flyback transformer today, everybody, all manufacturer of passive components, they are using nickel zinc material because you can use them up to maximum 2-3 megahertz with a very, very good core material. For higher frequency and for more reliability, we are using, and also other competitors are using nickel zinc material for the storage inductors. Now, if you don't want to use the inductor like a storage, you want to build a filter, then you have to concentrate and focus on the losses. The R are now your friend, and you have to take care now, because if you have a filtering problem at 500 kilohertz, you can see, 500 kilohertz, up to 1-2 megahertz, I can use iron powder core, but nickel zinc core is not so good because it will be not making losses. It will just make a delay, but not a losses. So for application and filtering for 200 kilohertz to maximum 1-2 megahertz, definitely I will use an iron core based inductor. If I have some noise at 10 megahertz and I'm still using an iron powder core, you will see that the filter will be not so successful working and you will not have any losses. But if you use a magnetic zinc core based inductor, 10 megahertz is excellent. Magnetic zinc core has its limit 20, 30 megahertz and then start to collapse very, very fast. At 60 megahertz, like here, wrote from my colleague from the marketing, 60 megahertz, definitely I will use a nickel zinc. I will not recommend at 60 megahertz to use a magnetic. The nickel zinc is much more better. Above 10, 20 megahertz, nickel zinc is the best core to be used for a filter inductor or choke because they have then a maximum about 100 to 300 megahertz. In this area, they have the absolutely dominance of the losses, but then also they start to collapse, and the absolutely limit of the frequency where you can still use is 2 gigahertz. If you want to filter something by 5 or 6 gigahertz and you think you can use a very low permeable nickel zinc, sorry, it's not possible. Physically, the lowest permeability, but we have something, a mu R by 15, give you at 2 gigahertz something like 8 dB insertion loss, but that's maximum. You cannot dream about 40 dB insertion loss with a nickel zinc ferrite at 6 gigahertz. This is impossible. What you can do, if you want to filter some triac thyristor switchers, then you can use these iron core-based inductors. If you want to filter for the conducted emission, 150 kilohertz, 30 megahertz, you can use this magnetic zinc core-based common mode chokes. And all these snap-on ferrites, 99% of the snap-on ferrites or the molded ferrites are made in nickel zinc. But what happened to these core losses actually? You know, in the physics we have this energy conservation law, and you cannot just put in a different universum the energy. You must to transform in some way. So actually this EMC noise or bad electronic noise, it gets transformed from the ferrite core into the heat. His losses make that this noise get into eddy current losses or magnetizing losses and transform into the thermal heat. But believe me, even if you use a very, very high sensitive, good thermal camera, and you will look on your USB cable or VGA cable and want to see this thermal heating generated by the EMC noise, it will be impossible because it's so small and it is just in a laboratory reproducible. If you ever produce a device, especially a power supply or something, and you put a ferrite core to the wire and this ferrite core start to run hot, then I want to say it is not anymore EMC problem. You have a safety problem, and I recommend run away fast you can because this is more like 10, 20 volts per meter. If you make the ferrite hot, it is 200, 300 volts per meter, and then this is a safety problem, not EMC problem anymore. Let's talk about some transmission mode and filter topologies. Well, if you go to the EMC lab, normally they tell you, hey guy, your device is working, but you have 40 dB above the limit. You have to do something against that. And you have the information, the frequency, 40 dB, but I want to know what is this 40 dB in terms of impedance for my ferrite or my filter. So the insertion loss formula, it is 20 times logarithm 10 by ZA plus ZF plus ZB divided by ZA plus ZB. What is ZA, ZB? Source impedance, load impedance. What you have to do, a little bit mathematics, take out of logarithms the ZF, this impedance of the ferrite, put this formula now in exponential. You just have to open the Excel file, type in, and press enter, and then, well, you will not have any result because this formula is working only if you know the source impedance and load impedance. And I'm asking you, how many of you, if you go to the EMC lab and you put your device in the EMC chamber to be measured, you know exactly what is the source impedance of your nose, or what is the load impedance where the noise is coupling in? Very difficult, very difficult. This is almost not so easy to do that. And what I realized that the young engineers which are coming from the university and they have a problem in EMC, they try to solve it. First of all, they start to simulate and then start to build some equivalent circuit that could be the noise source, that could be the load, and between a source and load, I will put a nice LC filter. Well, LC filter is a good point to start filtering something. For the inductance, you will get from us or from many other manufacturers as well, you get the replacement circuit, the parasitics, the spice parameter, S parameter, same from capacity we deliver, S parameter, everything, and then even simulation for simulation tool, you can start to simulate. But my opinion is that if you start to solve EMC problem by using a simulation tool, it is a lot of wasting time. Because I can imagine that you can really completely simulate your noise source, or even to simulate your load for the noise, it will be very, very difficult. So I would suggest, if you want to use the knowledge from the university, start with a formula, but think where you have some issue to solve it. If you have to connect different ground plane, when you make a analog ground and a digital ground, and you want to put these two ground planes together, then the ZA and the ZB in this case would be of value something like maximum 1, 2 ohm. If you think that your ground plane is higher like 5 ohm or something like that, imagine you have at home, almost of us, we have something like a hi-fi system. And when you connect your speaker to your hi-fi system, on the back side of the speaker, they are scripted something like 4 ohm or maybe 8 ohm, sometimes even if you have a subwoofer, 2 ohm. And can you realize that it is speaker are screaming music or making boom boom at 2 ohm or 3 ohm or 4 ohm? And now you want to tell that a ground plane cannot do the same? Even you don't hear it, it is there. But that's the reason why I recommend try to keep the ground planes as possible in milliohms. Don't exceed 1, 2 ohms if you connect ground planes, because then you have a bouncing ground plane and you can put tons of ferrites or filter inside. It will not help at all. Plan good ground planes, because if you have a good ground planes, you have avoid already 80% of the EMC mistakes. If you're filtering something like VCC distribution power supply, then it could be a value for ZA, ZB something 10 to 20 ohm. If it's a buck converter, output is even less than 10 ohm. But for a good starting point of calculation, 10, 20 ohm is quite familiar. If you have to filter video, clock, or data line, 50 to 90 ohm is very, very useful. USB port, if you think just on the USB port, you want to filter the USB data lines. USB data lines have something between 90 to even 210. If you have very, very, very long data lines, that can be even higher, like 150 ohm. Now, with this knowledge, you know now in which area you want to filter the ground plane, you want to filter the power supply. You can start and think and use the first filter. But now, even if you want to implement the filter, you have to think which filter you have to implement if you have a source side impedance low and a load side impedance high. Because then the best filter will be a LC filter. If you know that both sides are very high system impedance, a C or capacity, it will be the best solution. If you're not sure it is high, but how high, I don't know, I would suggest use a P filter. If you know that it is a low source impedance and load impedance, and else is not enough, you can give him a second L, and then you build your T filter. Now, be aware that if you're using kind of inductance and capacitors, the capacitor should be not couple microfarads. Use nanofarad, maximum 1 microfarad, and use inductors not with a high Q factor. Don't forget the Q factor of the inductors. Q factor quality means not it was made in Germany. It means that the dominancy XL to R, it is R dominated, so very, very low Q factor. If you put a high Q factor domination of XL at this frequency where you want to filter and less R, it will make more bad things because it starts to ringing. The filter starts to ring with the noise. So think about this different component, the self-resonant of the used components. Use low ASR, low ASL capacitor with a maximum 1 microfarad. Where the noise is coming? Well, this is always a nice question. Where is the noise coming from? And nobody can answer it. Sometimes you find out by yourself if you use a spectrum analyzer, the near field zone, and find out, okay, this is a DC-DC converter. Well, a DC-DC converter can make a lot of noise if you're not taking care about this different point of view. First of all, this is an example for a buck converter. A buck converter is very aggressive on the input. So you will generate on the input a conducting emission because the current doesn't be taken continuously. It will be switched on and off. It will charge in the inductor and the capacity. And at the same time, because on the output, you'll not deliver the current from the battery, you discharge your LC and the diode through the diode. You will have also some ripple current on the output. You will have also some conducting emission on the output as well. The most dangerous thing what you making here, actually, you charge the input capacitor for your DC-DC converter and transfer the energy through the switch to the inductor to the output capacity. So actually, you have a transfer of the energy from input capacity to the output capacity. And this track, this ground track from C in to C out, including the diode, this is the most dangerous track on the PCB side, where if you don't take care and press this crazy button called auto-routing, it will generate a lot of radiated emission. I will rename in every PCB routing software the auto-routing button to make EMC problem button. Don't press this button. Make this routing by yourself and keep short as possible, low impedance as possible. In my previous job when I was design engineer, I had a nice tutor which was also a guy, old guy, and he told me if directly lighting hit my device, it should go to this track and should not suffer. And then you can tell this is a low impedance, this is a good for the EMC. Now, point of view of the input of the buck converter, you have always the input capacity. This input capacity you can read from the data sheet what is the ASL, what is the ASR, and if you know also the input parasitics like inductive parasitics and resistive parasitic, with a very simplified formula, you can already calculate the expected noise on the input. This is quite very simple if you want to just pre-estimate which kind of noise you can expect already on the input. Second point on the output, again, you have to take care, you have a diode. The diode is also not the ideal diode. It has also some parasitics in ASR and ASL. And then also the output capacity is also not the ideal component, has also some parasitics. We don't talk about parasitics of these inductors because it's also not the ideal component. But at very, very high frequency, you will see here a resonance circuit. If you look with your scope, this ringing when you switch on and off, you will see this ringing that comes in a very high frequency exactly from this area. Additional, if you want to filter something on input, I will recommend at least put a small inductor value. A small low Q factor inductor, this is the minimum recommendation if you want to filter a buck converter. But please don't put here inductors in values of millihenries, because if you put a very, very big inductors in millihenries, it may suffer the input capacitor that will die hungry, because the inductor is always against a change. As soon the capacity needs to be charged, the inductance will slow down the current flow, and the input capacity will be out of function. So the input inductor value, actually here it's a value between 2.2 microhenry to maximum 22 microhenry. Very, very rare you will go up to 47 microhenry. If you want to do something more additional and you want to have a very good input filtering, you can even use this calculating, very simplified calculating input inductance value. I have here an example for a DC-DC converter with an output of 5 volt, output of 4 amp, switching frequency 2.5 megahertz. I know the ESR. I will calculate now the inductance value, and I will get the result of something like 320 nanohenry. You will see that 320 nanohenry is not a typical standard value. Choose the closest possible value. In this case, I would choose 1 microhenry. That will be my first start for the input inductance. Additional, you have to take care about the rated current. At this rated current, which is coming to the inductance on the input, the inductance should be not saturated at all and should not running hot. So I will do like expected efficiency of minimum 80%. I will even suggest to use higher, like 80%, but 80% is a good starting point. And in this case, if you use the simplified formula, you will need at 80% efficiency inductance with a maximum rated current of 1.25 amp. It means at this 1.25 amp, the inductor should not run in hot, and also you have to take care it should not saturate at all. Not 90% saturation, maximum 10% saturation, or even less. It's much more safety. If you want to extend the frequency of this filter on the input, and you want to make also for high frequency something additional, I recommend to use a chip bit ferrite in additional with the input filter, and put a second capacitor additional here, a value between 220 pico to maximum 1 nano, low ASR. And now with this T decade or P decade, you can have a very, very nice input filtering for differential noise. We're talking still about differential noise. That will not affect the common mode noise. It's only for differential mode. The same filter what you use in the input, you can multiply as well on the output if it's a boost converter. A buck converter, like I told you before, it is very aggressive on input. A boost converter is more aggressive or more noisy on the output. You can just mirroring everything like I told you, also the same way to the output filter if it's a boost converter. Now, if you want to do something against common mode noise, then I will recommend for common mode noise to use a common mode choke. A common mode choke can be used on input as well, but be aware that you will have here ground shifting. So you will have an outside ground, outside of your device, and an inside ground. The inside ground of your device, it will be after the common mode choke, and I recommend to use a common mode choke with not bifilar winding, with sector winding. The sector winding you can recognize sometimes the manufacturer like Würth Elektronik, we add additional letter like S Sierra, it means sector winded, or even in the data sheet you can see the ring is toroidal ring, and this is wound one side, the other side, two different inductance. These two different inductance sector winding give you automatically a higher leakage inductance. In this case, the leakage inductance is not bad, because if you put additional one capacity in front of him with the other capacity from the input from the DC-DC converter and the leakage inductance of this common mode choke, now you have a LC filter in differential mode, and you have a common mode filtering as well for common mode noise. That's the best thing if you can use this separation of outside ground and inside ground. It's not always possible to do this, and if you are not 100% sure and you cannot guarantee that the outside ground and inside ground are different, then you cannot use a common mode choke, because else you make a short on the one winding, and beginning of that point, if you have this short on the common mode choke, the common mode choke is just a heavy product on your PCB, but no function at all. What is the big difference between a shielded and unshielded inductance for a storage capacitor, for the storage inductance in a DC-DC converter? Well, first of all, in the manufacturing, for the unshielded inductance, we use a ferrite bobbin core, and then we wound some wire on the core. And if you make a magnetic cut exactly in the middle, you can see the core shape here, and the biggest magnetic field is close as possible to the wire. Then this magnetic field escapes from the core, like here, you can see on the picture on the right side. And the big difference to the shielded one, we put around this bobbin additional shielding ring, also from ferrite. We will have a small gap on the top and on the bottom, but then you will see that the biggest magnetic field will turn back through this shielding ring, again back into the core, and you will have a very, very small leakage of the magnetic field of this shielded inductor. That makes a lot of sense in a DC-DC converter when you are doing that in the EMC lab, and you will see a massive difference. I can show you here an experiment which we did done here in Germany, Waldenburg. We took a 2 megahertz DC-DC converter, and we used for our storage inductor 10 microhen inductance. It was a 1 amp output, and we did measure the conductor emission on input. We did not mention any EMC limits here, just mark where is the maximum, and then don't change anything on the setup. Just take a soldering iron, desolder the unshielded inductance, and solder instead a shielded inductance. And what you can see, wow, it's a big difference. Only just because of the shielding, you will have less conductor emission because it will not contaminate this big emission from the unshielded choke in comparison with the shielded choke, and you will have already 19 dBm less to fight in the conductor emission. Because of that point, I always recommend for the storage inductance, please use shielded inductance. Much nicer was the experiment in the EMC chamber. If we put that in the EMC chamber and scan for the emission, you can see by the picture the unshielded one has a lot of high peaks against to the shielded version, where we don't have to fight so much against this massive emission. So because of this reason, again, use shielded inductance for storage. Another nice experiment, given feedback from a customer. He did make a small power supply for an electrical motor, and he goes to the EMC lab. The lab measured the conductor emission. He failed. He was not so happy with this, but come back to us and ask what we can do to improve this EMC in conductor emission. First of all, we saw he used a double-side PCB. He used some rod core inductance. We say, okay, how about the idea to use, instead of this rod core inductance, to shielded inductance, and the empty area on the top side float with ground and make nice vias to the bottom ground, and let me see what will happen. Don't change anything on the schematic, in fact. The customer did implement our recommendation, change this inductance to shielded one, float the ground, result. In fact, the EMC guy in the laboratory, when he saw his schematic, version 1, version 2, he said, well, I don't see any filtering on your device. Why I should start to measure? Why I should waste your money to measure again this PCB? And he said, yeah, because maybe it's just a change, because this shielded inductance is much better. And in fact, it was much better, with a very, very simple solution in the dramatic result. This is nice when the EMC guy gets nervous, because he can't believe it that it's so much. I like that when the EMC guy gets nervous. I don't know why. Well, if you want to know more about magnetics, I will recommend this book, Trilogy of Magnetics, which you can win today. There are many applications described in this book, and it's written not from professor from university. It is written and collected from different design engineers and also from EMC labs, and it's a good tool to use this one. If you want to get any support or samples, Farnell is a good choice. You can try to get the samples very fast from Farnell, next day delivery. In the most countries, we have always our own FIEs. Just please contact us, and we will give the best support worldwide. So that was from my side. Don't forget, please, to participate to our quiz. This is a very simple question. I think I will not make your life so difficult if you want to answer these two questions. If you answer to these two questions, already you have the possibility to win one of these books. And yes, I very thank you for visiting my webinar, and I will be very happy if we get in contact, whatever about element 14 or about Twitter. We will give you our best support to you. So now I'm looking for any questions. If some question from the presentation. If you have any question, please just put in the Q&A or on the chat. I will try to give my best. We still have 40 minutes for the WebEx.